So let's plug in our values here for our midpoint. If we plug those in, what are we going to add here in the numerator using these two coordinates? Say it again. Good, because it's 2 plus a negative 4, which just is 2 minus 4, divided by 2, comma. And what are we going to plug in for the y's? 8 plus 6, and then divide by 2. So if we simplify that, what is 2 minus 4? Negative 2 divided by 2, negative 1. And then what is 8 plus 6? 14 divided by 2, 7. And make sure when you write your answer as an ordered pair that you are putting parentheses around it. Some of you have left off those parentheses. An ordered pair needs to have parentheses around it, okay? You will have to be able to find the midpoint in this lesson today. So super important you understand how to find the midpoint. And then slope. Slope. Well, how do we calculate slope if we don't graph it? Close, Bailey, but you have it flipped. It's not run over rise, it's rise over run. So what should be on the top? Y. When you think about your rise, you're thinking about the y-axis. So y's always go on top. So your slope is y2 minus y1 over x2 minus x1. You can graph it. I want you to try to get away from that method as much as possible, because next year when you get to Algebra 2, and the math gets even harder, you're not going to have nice, pretty ordered pairs that can always be graphed to then calculate your slope. It is not wrong, and it is totally fine if you're working a problem in geometry and it's easier for you to graph it and calculate slope. I won't count it off. I'm not saying that you can't do that. I'm just saying if you want to get better prepared for Algebra 2, you need to know your slope formula, okay? So slope, change in y over change in x, rise over run. So if we plug in our coordinates, what's going to go on the top here? Six minus 8. Okay, 6 minus 8 over negative 4 minus 2. Good. Okay, so be real careful with your signs there. What is 6 minus 8? Negative 2. And what is negative 4 minus 2? Negative 6. Make sure you're subtracting, not multiplying. And then what is negative 2 divided by negative 6 when we reduce that? Positive 1/3. The negative over a negative becomes a positive, and 2 goes into both 2 and 6. So your slope is 1/3. You're going to have to be able to calculate your slope in today's lesson. Any questions on midpoint or slope? Okay, so I skipped the first two because you're not going to have to do constructions in this lesson. We are going to talk about a perpendicular bisector and an angle bisector, but I didn't want to take the time to go over those constructions. We are going to review what is a perpendicular bisector and what is an angle bisector. This section is all about two theorems, just two theorems, and that's all there is to it. I'm going to warn you, Chapter 5 is long. And just like Chapter 4 was long. So I don't know how you felt about the test when you took it, but there was a lot of information to remember for Chapter 4. Would you agree? We had proofs, we had transformations, we had all of the different theorems about exterior angle theorem and triangle sum theorem, and then trying to apply all of that to your problems, and then all the different proofs that we had that went with that. Chapter 5 is going to probably feel the same way, and then we're going to take a week off in the middle and go away and not do geometry for a week, and then come back and have to remember everything we learned this week. So it's going to feel a little bit overwhelming at times. There's a lot of information. There's 8 sections in Chapter 5. So I'm just going to warn you that you're going to want to make sure that you're studying a little bit at a time. And my best advice for you would be Sunday night, before we come back after Thanksgiving break, if I were you, I would pull out my notes and just go back through. What did we learn in 5.1? What did we learn in 5.2? What did we learn in 5.3? Try to get your mind wrapped back around what we did prior to going away for Thanksgiving break. Because then when we come back, we will have a short little bit of time in class to review, and then we've got to move on to 5.4 and get going. So we won't have like a full day come back from Thanksgiving and let's review everything we learned before we went. And there is just a lot of theorems in chapter 5. And so trying to keep everything straight. And I'm going to do my best to give you some tricks, some acronyms, some things that might help you organize the different theorems. But there's a lot of theorems in chapter 5. This will be our last test for the semester. We will have a vocab test that will be a lot easier probably than the other ones because there's only 13 vocab words in chapter 5. I believe there's only 13. So it should be short for you. And then we'll have the vocab test and the chapter test, and then the semester exam. So there's very few grades left to go in your grade as well. So it's going to be important that you are doing the best that you possibly can on the homework and on these quizzes and tests coming up, okay? All right, so perpendicular bisector, angle bisector are what this section is about, and just those two theorems. I should warn you too, when you're studying for that vocab test, you'll see at the end of the chapter, if you look there, that this word locus is on there, but it will not be on your vocab test. And I'll give you a review like I always do, so you won't have to worry about that. Okay, so two theorems that we're going to learn today. The first one is the perpendicular bisector theorem. And the second one is the angle bisector theorem. So I'm going to write this up here just so we can refer back to it as we're going through the lesson today. So first of all, I didn't have you do the construction, although some of you were remembering how to do that. If we had, back in chapter 1, if we had a line segment, AB, we didn't call it a perpendicular bisector in chapter 1. We called it a segment bisector. But when we did that construction, we ended up creating a line that went through a line segment. What point did it go through here? The midpoint. Because it was a bisector, it split that line segment into two congruent parts, right? We never said that it was perpendicular, but it was always perpendicular. What's it mean to be perpendicular? Okay, it makes a right angle. So when we did that construction back in chapter 1, it made a right angle. We just didn't talk about it making a right angle. So when they say perpendicular bisector, it's going to have two characteristics. It's going to make a right angle, and it's going to bisect the line segment. Okay? So that's just the review from chapter 1. And then in chapter 1, we also did an angle bisector construction. So when we did it, we created a line that went through, or a ray that went through our angle. And when we did that, it split the angle into two congruent parts. Again, you won't have to do constructions for this chapter, but you need to understand those words, angle bisector and perpendicular bisector. Any questions so far? Okay, so before we look at the two theorems, there is this vocabulary word, equidistant. I want to make sure you understand what it means if they say a point is equidistant to two objects. So when a point is the same distance away from two or more objects, we say it's equidistant. So I could say that I am equidistant to both Jackson and Jacob, right? If I'm the same distance from them. So I could be a point, they could be two objects, I'm equidistant from them. So anytime you see that equidistant word, think same distance. Okay? Right, first theorem, perpendicular bisector theorem. The problems are not going to be hard mathematically, like the whole lesson today. The math, the actual number solving, not hard. The theorems are going to be the part that you have to really get clear in your mind. If you understand the theorem, the math behind it's really easy. So first theorem is the perpendicular bisector theorem. Here's what it says. It says if you have a point on the perpendicular bisector of a segment. So first of all, looking at this picture right here, what line is the perpendicular bisector? Okay, so I heard L, I heard up and down, I heard X, Y. Those are all the same thing. Does everybody agree that this line right here is our perpendicular bisector? It's making a right angle, and it's splitting this line segment into two congruent parts. The key in this chapter is going to be looking at your markings. You're going to have to look at those markings and ask yourself, what does that tell me? So if it's perpendicular and it's bisecting, then that line is your perpendicular bisector. Okay, so if you have a point on the perpendicular bisector, so like point X, if that point is on the perpendicular bisector, then that point will be equidistant to the endpoints. That means that point X will be the same distance away from A as it is from B. Or that XA is now going to be equal to XB. Any point on your perpendicular bisector will be equidistant to your two endpoints. That's what this theorem says. So again, I'll show you up here on the board. Any point, so I could pick a point down here and draw the distance to the endpoint, draw the distance to the endpoint. Those two distances will be the same. I could pick a different point somewhere else on that line. The distance from that point to A and that point to B are not necessarily the same as the green distances, but they will be equal to each other. So these two will be the same distance, these two will be the same distance. Is that making sense? Okay. The second part down here is just the converse. Remind me, back in chapter 2, what does a converse do to your theorem? Okay, it switches it. So instead of saying if P then Q, what does it say? If Q then P. So this said if you have a perpendicular bisector, then a point is equidistant. This is going to say you don't know you have a perpendicular bisector. Look at the picture. See if you see on that picture. Do you see a right angle box anywhere? Nope. Do you see that the segment has been split into two congruent parts where you have a line segment? Careful, line segment? No. These pieces are congruent, but those are not one line segment split into two congruent parts. So this line AB is not split into two congruent parts. There is no right angle box. So we don't know that we have a perpendicular bisector. But we do know that this point X is equidistant to the endpoints. So it's just going backwards. If these are equidistant, then this line must be a perpendicular bisector. So the converse is just going to switch it. I don't know that this is a perpendicular bisector, but now that these are equidistant, I can say that XY must be a perpendicular bisector, which means I can say that this must be a right angle. So XY must be perpendicular to AB. And I can say that it's a bisector, which means YA and YB must be the same length. Are you guys with me on just going backwards? So up here on the board, I'll write that to show you the difference. So the converse of this theorem is going to say, here's a line segment. You don't know this is a perpendicular bisector. You're given that this distance is the same as this distance. Therefore, you can conclude that XY is what? A perpendicular bisector. So we can say XY is a perpendicular bisector. That's what the converse would do. Goes the other direction. Okay? So let's look at some problems where you have to apply that. So look at the picture. Again, the hardest part to me on chapter 5 is understanding what do I have here, because there are no words that are going to say perpendicular bisector or angle bisector. When you look at the picture, look at the markings. Do you see the right angle box? Do you see the two congruent markings? What does that mean about line UW? It's a perpendicular bisector. Does everybody agree with that? Okay, so what does the perpendicular bisector theorem tell me then about this picture? Very good. It makes the two sides equal, so UT and UV must be the same length. Okay, and then once you see that, what can we do algebraically then to solve for x if those are equal? Okay, so what would I write, Reese? Exactly. So all you're doing is looking at the picture, asking yourself, what do I see in my picture? What does that now mean because of that theorem? And now that you have the theorem figured out, you know those two sides are equal, you just set up your algebra equation and solve. And the math here should be pretty easy because it's not really hard, quadratics, factoring, all of that. It's not a proof. No, we're not doing any proofs right now. Okay, so let's solve. What do I do? What do you want to do to solve? Subtract 3x. So we have 9 equals 4x minus 17. What do you want to do next? Add 17. So 4x is equal to 26. And then lastly, we'll divide by 4. And what is x? 6.5. Is that our answer? No. Read your directions. Be really careful. What did it ask us to find? TU. So now you go back to the picture. TU was this side over here, which is the 3x plus 9. So we're going to plug that back in. TU equals 3x plus 9. Plug in your 6.5. And what do we get? We should end up here with 19.5 plus 9, and then that gives us 28.5. Do I put a line segment above TU? No, never when you're telling me what it is equal to. Questions on perpendicular bisector theorem? Make sure I don't go too fast. So you flip your notes over. If you look at the next one, same kind of idea, but just worded a little different. So when you look at the picture, does the picture show me that I have a perpendicular bisector? No, it shows me I have a line that is what? Perpendicular, but do I have any bisecting marks? No. But if you go to the directions, it says, given that line L is the perpendicular bisector. So now the first thing I would do is mark my picture. If line L is the perpendicular bisector, what two parts can I mark congruent? DF and EF. Yes, I can mark those two pieces congruent because now it is not only perpendicular, but it's a bisector. And now using our theorem, what else can we mark congruent? DG and EG. Very good. So now we can mark these sides congruent. And then we can finish filling in what it tells us. It says that that EG is 14.6. So EG is 14.6. Write it on your picture. They want you to find what? DG. And that should be super easy now. What is DG? Just 14.6. So like I said, the math part, the actual solving is not going to be hard. It's just, do you understand what you have in your picture? Can you understand the markings? Do you know what you can say is congruent? And if you do, then the math behind it's really easy. Any questions on perpendicular bisector theorem? Okay, let's move on to the next one. Okay, so before we do angle bisector theorem, there is this little remember slide that's in your notes. So it says, remember that the distance between a point and a line is always the perpendicular segment. So think about this with me. If I say, what is my distance from me to that wall? Should I walk diagonally towards Nathan and measure my distance? Or should I walk straight to the wall and measure my distance? Straight, right? So anytime you're talking about what is the distance from a point to a line, you don't want to measure that distance diagonally. You want to measure that distance perpendicularly, meaning that you should look for the distance from that point to that line that makes a straight line, perpendicular right angle. Does everybody understand what I'm saying there? So shortest distance, not the longest distance. So keep that in mind in this next theorem. So the second theorem today is the angle bisector theorem. Okay, once again, it's going to start with if a point is on the angle bisector. So if a point is on the bisector of an angle. So when you look at the picture, do you see an angle that has been bisected? Which angle in that picture has been bisected? Angle P, angle APB, the big angle, right? It's being split into two congruent parts. So first you have to have an angle bisector. If you have an angle bisector and you have a point on that angle bisector. So what is the ray that is actually the angle bisector in the picture? What is the ray? Say it again, Reese. CP. So this ray PC is actually our angle bisector, right? It's the one splitting the angle into two congruent parts. What is a point on that angle bisector? P is what else? C. So if you have a point on that angle bisector, this theorem says that point will be equidistant from the sides of the angle. But when you draw the distance, you need to make sure that you're drawing it perpendicularly. So what they're saying is that from C over to this side of the angle, so that would be this perpendicular distance, and from C over to this side of the angle, which would be this perpendicular distance. Those two distances will be the same. But it has to be drawn perpendicularly. Here's how they'll trick you. So first of all, do you see an angle bisector in this picture? Okay, the angle down here has been split into two congruent parts. So according to this theorem, the distance from this point, I'll call it A, over to each side should be the same, right? But does that mean that X is 7? We want to say yes, right? Because those are both going from A over to the sides. But what's wrong with this picture? Why are we not sure that it's 7? Okay, it's not marked as a right angle. So this could be drawn diagonally, which would make it longer than 7. If it is drawn perpendicularly over to the side, then it is for sure 7. But if it is drawn diagonally, it could be longer than 7. So you have to have the right angle boxes when we're talking about those are equal distance. Does that make sense? So be really careful on the homework. If they ask you, are these both the same? Do they both have right angle boxes? If they do, then yes, they're the same length as long as you have an angle bisector. Okay? Don't let them trick you. All right, so then there's the converse. So I'm going to go ahead and mark up here what this theorem said. This theorem says that the distance from any point on the angle bisector over to the sides will be the same. But just make sure that it's drawn perpendicularly. So the converse is just going to switch it. The converse is going to say you have an angle, but you do not know for sure that it has been bisected. So there's no markings down here saying that the angle has been bisected. But if they tell you this distance is congruent to this distance, then what does that mean about ray AC? It must be an angle bisector. So it's going to go the other direction. If the distances are congruent, then this must be an angle bisector. So then we could conclude with the converse that AC is an angle bisector. And that means we would know then that those two angles are congruent. Does that make sense? Okay, let's look at some problems. So here's the first one. So first thing I would ask you to do is look at the picture and ask yourself, what do the markings in the picture show me? So in this picture, we see that we have this point M, and it is congruent over to this side and over to this side. So those things are marked congruent and they're perpendicular distances. So what is that going to tell me about this picture? Very good. It's going to tell me then that this ray, KM, must be an angle bisector. So which angles are going to be congruent? JKM and LKM. So everybody see how that ray then is going to split that angle into two congruent parts. Is this the angle bisector theorem or is this the converse of the angle bisector theorem? Converse. So notice the converse is you don't know that it's perpendicular bisector or angle bisector, but that's what you're concluding. Okay, so now that we know that these are congruent, what could we write down using algebra to solve for A? Good, Chris. 3A plus 20 is equal to 2A plus 26. Because we're saying those two angles are congruent, so they must be equal. Okay? So somebody tell me what you want to do to solve. Subtract 2A. So A plus 20 equals 26. What do you want to do from here? Subtract 20. So what is A? 6. Is that our answer? No. What does it want us to find? Measure of MKL. So go to your picture and make sure you know which angle that's referring to. So you put your pencil at M, go to K, go to L. So we're looking for this angle right here, which is the 2A plus 26. So the measure of angle MKL is equal to 2A plus 26. Plug in your value for A, which was 6, and solve. What's 2 times 6? 12. What's 12 plus 26? 38. And 38 what? Degrees. Don't forget your degree symbol. Don't forget the little m when you're giving me the measure. So measure of angle MKL is 38 degrees. Questions on angle bisector theorem? Okay, if you flip it over, same kind of problem again. This one's just a little bit easier, but first thing I would do is have you look at the picture. Based on the markings in the picture, do we have an angle bisector? Just looking at the picture. I don't see any angle that's been split into two congruent parts based off of markings. Do you? No. Do we have congruent distances in the picture? Careful, we've got some distances, but are they marked congruent? No. Based on this picture, we don't have either of those things. But if we read the directions, it says, given that YW bisects angle XYZ. So now we need to mark that in our picture. YW bisects which angle? XYZ. So put your pencil at X, go from X to Y to Z. That's the angle that's being split into two congruent parts. So which two angles are we saying are congruent here? XYW, this angle, and ZYW, this angle. Does everybody see the angle based on what it was saying in the directions? Okay, now we do have an angle bisector. So what else is going to be congruent according to the angle bisector theorem? Okay, X and Z are points. So what do you mean as far as distances? We don't know that X, Y, and YZ are congruent, so be careful here. Reese, look at your picture. If the angle's been bisected, then it's a point that's on the angle bisector, and it's a distance from that point over to the sides that we can say are congruent. Not that these distances that are making the angle are congruent. So what are the distances in this picture that would be congruent? Okay, so if this is the angle bisector, which is what they told us, YW bisects the angle, then the point that's on that is W. So the distance from W over to the sides, those are the distances that will be equal. Does everybody see that? So these are now congruent, and we can mark them congruent. Questions? Still confused on what you can mark? Okay, so then we go back to the problem, and what do they tell us in the problem? WZ is 3.05. What do they ask us to find? So what is WX? 3.05. So once again, the math, not hard. Understanding the theorem becomes the harder part. Do I have an angle bisector? What distances are now congruent? Questions? Okay, we're going to skip the next one, the parachute question, and go on down to the last one there. So the last question here that you're going to see is going to take us back to the bell work. And you're going to need a piece of graph paper. So if everybody will jump up, grab some graph paper. And you'll need it for homework too, so make sure you have graph paper in your binder. Here, I can get you some, Reese. You don't have to do all that. How many pieces do you need? Okay. Sorry, I'm jumping in front of you. I keep thinking I'm grabbing more than I am. There you go, bud. You're welcome. Sorry. Okay, once you have your graph paper, then join back up with me here on example 4, and let's make sure that you understand even what it's asking, because sometimes it can get kind of wordy. So it says write an equation. So our goal here is to write an equation in point slope form. So this takes us back to chapter 3 and back to algebra 1. What is point slope form, first of all? Y. Okay, y equals mx plus b is not point slope form, but what form is y equals mx plus b? Slope intercept form. This one says point slope form. So what's point slope form? Very good. So if you have forgotten point slope form, make sure you write that down and make a note that you need to memorize that. You do need to still know slope intercept form is y equals mx plus b, but this question said point slope form. So we're going to use point slope form. So remember back in chapter 3 when we learned and reviewed this form, we talked about how the great thing about point slope form is it doesn't matter which point you use. It can be any point that's on your line. So that's why I think it's better than slope intercept form. Slope intercept form requires you to use the y-intercept. And so sometimes that's not a very pretty number or easy to find. But this lets us use any point that's on our line. So we're going to need to find a point and plug it in for x1, y1. And then we have to find our slope. Okay, so that's why we did the review of slope formula back in the bell work. Okay, so it wants us to write an equation in point slope form, but be careful that you read the rest of the question. For the perpendicular bisector of. For the perpendicular bisector of this segment that they're giving you here, C and D. So are we writing an equation for the line segment CD? No. We're not writing the equation for CD. We're writing an equation for a perpendicular bisector of CD. So let's graph CD first, and let's make sure we can see what we're talking about. So take your graph paper, graph points C and D, and make a line segment. Remember, your points are always x, comma, y. So graph 6, -5, 10, 1, label it C and D. Okay, so again, we're not writing an equation for this line segment. That's like up here where we started the lesson. That's the line segment. We're trying to write the equation of the line that would go through that line segment and be a perpendicular bisector. Okay, so remind me, the perpendicular bisector goes through what point on your line segment? I'm hearing a couple of people say it. Are you guys with them? This line goes through what point? The midpoint. So again, in the bell work, we reviewed the midpoint formula. So we're trying to write an equation of a line that's going to go through CD somewhere and it's going to be perpendicular to CD, and it's going to bisect CD. So we know for sure the first thing we need to find is the midpoint of CD, because we know it's going to go through the midpoint of that line segment. It's going to bisect the line segment. Okay, so let's find the midpoint of CD. Midpoint formula we reviewed in bell work. We're going to add the x's, add the y's, and then divide them both by 2. So what am I going to add to start with for my x's? You're using C and D to find its midpoint. 6 plus 10 and divide by 2. Okay, what do we add for the y's? -5 plus 1 and divide by 2. Okay, so midpoint is just the average of your x's, average of your y's. 6 plus 10 is how much? 16 divided by 2, 8. -5 plus 1, -4 divided by 2, -2. So that means our midpoint is at 8, -2. Go to your graph and make sure that that is correct, that it lands on CD, that it's at the midpoint. So if you go to 8, -2, is it on CD and does it look like it's at the midpoint of CD? Okay, then that'll help you visually make sure you didn't make a mistake when you did the midpoint. Okay, so again, we're trying to write the equation of the line that's going to go through CD, be perpendicular to it, and bisect it. So we know for sure that our line's going to go through M. So what am I going to do with this 8, -2 when I write my equation? Where's that going to go in my equation? In the x1 and y1, right? Because it is a point that is going to be on my line. My line needs to go through M, and it needs to be perpendicular to C. It's going to bisect it and be perpendicular to it. So basically what we just found right here is a point on our line, x1, y1. So we're just going to plug that into our equation. Okay, what's the second thing we need to find in order to write this equation? The slope. Do we want the slope of CD? No, what do we want the slope of? Of the perpendicular bisector. So what did we learn back in chapter 3 about perpendicular lines besides that they make right angles? Very good. Their slopes are opposite reciprocals. If they're perpendicular, their slopes are opposite reciprocal. So what we need to do, second, is find the slope of CD, but we don't want that slope. Then we'll find the slope that's perpendicular to it. So remember, that is the opposite reciprocal. Okay? So we'll start by finding the slope of CD, and you've got it graphed on your paper. So this would be one time where it's probably easier just to count the rise, count the run. So what is the slope from C to D? Okay, I'm hearing 3/2 because you went up how far? I think you went up more than 3. You went up 6 and you went over how far? 4. Okay, so it's really starts out being 6/4, but then you reduced it to 3/2. You do have the midpoint. You're right. So you could have done up 3/2. You're right. You could have went from C to the midpoint. Is everybody with either direction there? 3 up 3 right 2 or up 6 right 4 is still 3/2. Okay, but again, that's not your slope. That's the slope of CD. We want the slope of the line that's perpendicular to it. So what is our slope going to be? Careful. Opposite means change the sign. What does reciprocal mean? Flip it. So what is it going to be? -2/3. You have to change the sign from positive to negative, and then you have to flip the fraction. Opposite reciprocal. So now we have our slope, and we have our point, so we can plug it into our point slope formula. Okay, so we found the midpoint to find a point on our line, and then we found the slope, and we flipped it and changed the sign to get the perpendicular slope. And now we can plug it in and write an equation, because our goal was to write an equation. So what am I going to have here for the left side? Okay, so be careful. It's y minus, but then what is our y1? A negative 2. So what's minus a negative? A positive. So it's going to be y plus 2 equals negative 2/3. Plug in your slope. Make sure it's the opposite reciprocal slope. And then what are we going to have in parentheses? X minus 8. And this is the equation of the line that if we were to graph would be perpendicular to the line CD and it would bisect CD. It is our perpendicular bisector. Questions on the perpendicular bisector theorem, angle bisector theorem, or how to come up with this equation? All right, 3 big ideas for 5-1. Go to 5-2. Okay, so 5-2 is going to introduce us to what are called points of concurrency. And we're going to learn 2 points of concurrency in 5-2. And then Friday, we're going to learn 2 more points of concurrency in 5-3. And even though I have on the board that we're going to do 5-3 and 5-4, we probably will only do 5-3 on Friday, depending on how much time we have. So you will have an assignment on Friday. I know that we're going away for Thanksgiving break for the week, but you will still need to do that assignment. And my advice on Friday will be to do it Friday. Do it right while it's fresh on your mind. If you wait, it won't be due until the Tuesday we come back from break. If you wait till Monday night to try to do that assignment, it is going to take you so much longer because you're going to have forgotten so many things and you're going to be trying to go back and figure out how did we do this? What did she say? And you would get it done so much faster if you can do it Friday right after class. Okay, so as soon as you can Friday or Saturday, do your homework from Friday. And that way, Monday night before class on Tuesday, you're just reviewing and getting ready for class. Not having to try to do an entire assignment that you've forgotten about. Okay, so 2 points of concurrency in 5-2. What are points of concurrency? What does that mean? So basically what this lesson is going to do is it's going to take these 2 ideas, a perpendicular bisector and an angle bisector, and it's going to put them in a triangle. So a perpendicular bisector bisects a line segment, right? If I draw a triangle, how many line segments do I have? How many line segments are in a triangle? 3, right? There's 3 sides, okay? How many angles are in a triangle? 3. So what I can do and what they're going to do in this lesson is they're going to take this triangle and they're going to draw in all 3 perpendicular bisectors. And then they're going to take that triangle and they're going to draw in all 3 angle bisectors. And we're going to see what happens when we do that to a triangle. So before we get there, let's talk about a couple of vocabulary words. And also let me clarify, what does a perpendicular bisector look like in a triangle? So if you have a triangle, let's say I have an isosceles triangle, and then let's say that I have an obtuse triangle. I want to show you that it works some of the times and not all of the times. If I draw in a perpendicular bisector, that means I'm going to pick one side of my triangle. I'm going to estimate about where I think that midpoint is, and I'm going to draw a line that goes through the midpoint and makes a right angle. Did my perpendicular bisector go through the vertex of the triangle? Okay, yes, it did. But go to your obtuse triangle. Pick a side, estimate about where the midpoint is, and draw a line that makes a right angle. Did it go through the vertex? No. So this little helpful hint is just reminding you that a perpendicular bisector does not pass through the opposite vertex all the time. Okay, it can, but it does not always pass through the opposite vertex. So you're not worried about it going through the vertex. You're worried about the 2 things we just talked about. It's got to go through the midpoint, and it's got to make a right angle. Okay? All right. So before we actually do that to a triangle, let's talk about what does it mean to be concurrent and what is a point of concurrency. So anytime you have 3 or more lines and they intersect at the same point. So for example, the picture I just drew, do you see how I have 3 lines and they all intersected at the same point? then we say when 3 or more lines intersect at one point, that those lines are concurrent. Concurrent means they all intersect at the same point. So in the classroom, take the ceiling and the wall. Do you guys see this line where they meet? Okay. Take the ceiling and that wall. Do you see this line where they meet? Take these two walls. Do you see the line where they meet? Now take all 3 of those lines. Where do they intersect? Okay, up there in that one corner point, right? So those 3 lines are concurrent. They intersect at one point. That point then is called, so the point where they intersect is called the point of concurrency. So this little point right here is called the point of concurrency, where they meet. It's important you understand these vocab words. So concurrent means 3 lines intersect at a common point, and where they meet is called the point of concurrency. And we're getting ready to look at, between today and Friday, 4 different line segments that make 4 different points of concurrency, and each one of them is going to have a special name, and each one of them is going to have a special theorem that goes with them. Okay, and then we're going to have to try to keep that straight in our head, and I'll give you a little tool that I came up with that helped me. So first one we're going to talk about is perpendicular bisectors. So follow along with me up here on the board. I'm going to draw in all 3 perpendicular bisectors, and I'm just going to estimate them. If I really wanted to do this accurately, I would use my compass like they reviewed in the bell work, and we didn't do. I would use my compass and I would actually construct them. But I'm just going to estimate for time purposes. So I'm going to take this side of the triangle here. I'm going to estimate where the midpoint is, and I'm going to draw a line that's perpendicular through the midpoint. And again, it does not have to go through the vertex. It just needs to be perpendicular and bisect. I'm going to pick another side of my triangle, estimate where I think the midpoint is, and draw a line that looks like it's making a right angle. And then I'm going to do it one more time for this third side. So pick a side where you think the midpoint is, estimate that, and then I'm going to draw in the line that looks like it's making a right angle. And do you notice, if I did it really accurately and correctly, all 3 of those green lines are concurrent. They intersect at a common point. Do you see that? This point right here, again today, what's the general name for it? Point of concurrency. But now, because it's made by perpendicular bisectors, it's going to have a special name. That point is called the circumcenter. The circumcenter is the point of concurrency of the perpendicular bisectors. Point of concurrency of the perpendicular bisectors. It's called the circumcenter. So this point right there is called the circumcenter. Everybody with me so far? Okay. Circumcenter has a special theorem that goes with it. It's called the circumcenter theorem. The circumcenter theorem says that if you have a circumcenter, so first of all, let's look at this picture on your notes. What color of lines are the perpendicular bisectors? Which lines in the picture, which color are perpendicular bisectors? Red. Look at your markings. Do you see how each of those red lines are making a right angle and bisecting the side of the triangle? Okay, so notice that the red lines all intersect at what point? P. So P is the circumcenter. Okay, here's what this theorem says. The theorem says the circumcenter is equidistant to the vertices of the triangle. The circumcenter is equidistant to the vertices. That means if you go from P to vertex A, from P to vertex B, or from P to vertex C, those are all going to have the same length. PA is the same as PB, is the same as PC. So up here in my picture, I'm going to draw that in. This is my circumcenter theorem. It says the distance from the circumcenter to a vertex is the same length. Okay? And then they're going to try to make sure that you understand why that's true. So they're going to talk about what's called a circumscribed circle. So I'm going to draw a circle around my triangle here that touches every vertex. So the next thing you'll see in your notes, actually I'm going to skip ahead. Look here, do you guys see this circumscribed circle? Okay, a circumscribed circle is a circle that contains all the vertices of a polygon. Basically, it's on the outside of your polygon and it touches every vertex. So what do you notice if P is the circumcenter and these distances PA, PB, and PC are all supposed to be the same? In the circle, what is PA or PB or PC? The radius. And what did we learn a long time ago before you came to high school about the radius of a circle? Every radius is what? The same in the same circle, right? So they're trying to show you that you could draw a circle around this, and the circumcenter to the vertex then would be a radius, and all the radii are equal. That's why the circumcenter theorem is true. Okay, so the circumcenter theorem, make sure you're with me again, says the distance from the circumcenter to each vertex is the same. Okay, let's go back. On your homework, they're going to ask you some questions about the circumcenter. So here's a chart that will help you with that. So first of all, add to your notes, each of these lines are perpendicular bisectors. They don't tell you that here, but all of the lines are perpendicular bisectors. We could go through, if we had time, and draw in all the little right angles and the bisector marks. Right angles and bisectors, right angles and bisectors. Or you can just write it there. The lines are perpendicular bisectors. Okay? So what does that make this point P today? What do we call it if it's made by perpendicular bisectors? The circumcenter. Okay, circumcenter is made by the perpendicular bisectors. Where is the circumcenter when the triangle is acute? Okay, it's inside. Not necessarily is it directly in the middle, but it is inside the triangle. You may have an always, sometimes never question on your homework that asks you something about the circumcenter and an acute triangle. The circumcenter is always inside the triangle. Where is the circumcenter if your triangle is obtuse? Outside the triangle. Where is your circumcenter if it's a right triangle? It's on the hypotenuse. So if you get to the homework and you're like, I don't know where the circumcenter is, look back at your notes. And then if you get to the test in several weeks from now and you can't remember, sketch a picture of your perpendicular bisectors and see where does it land when it's acute? Where does it land when it's obtuse? I'm sorry, baby. Is it EGG? Okay, 9th or 10th, Barrett. What's the reason, Barrett? Okay. Okay, so I'll just put stomach headache. Okay, back up here, we still have quite a bit, guys, so focus with me for a few more minutes, okay? Any questions right now? All right. So let's look at what this might look like for a homework question. And again, I'm going to tell you, I think the hardest part of this is just being able to understand what do I have in my picture. You've got to look at your markings, okay? So first of all, now we're with the triangle. So turn and make sure you see you're on the same example as me. We've got a triangle. In the picture, as far as markings go, all we have are some right angle boxes here, right? But there's no bisecting marks. But if we go back up here to the directions, it says DG, EG, and FG are the perpendicular bisectors. So now go to the picture and let's mark what that's telling us. DG is a perpendicular bisector. What pieces can I mark congruent then? Okay, first of all, what I can mark congruent based off DG being a perpendicular bisector, that means it's perpendicular to one side of the triangle and it's bisecting one side of the triangle. So I heard somebody say it. What two pieces are congruent? BD and AD. This little piece is a perpendicular bisector of this side. Okay, go to the next one. EG is a perpendicular bisector. What can I mark congruent? BE and CE. Okay, the next one, FG is a perpendicular bisector. What can I mark congruent? AF and CF. So understand when it says perpendicular bisector of the triangle, it's saying it's bisecting the sides of the triangle. Okay, what does that make point G according to today? The circumcenter. The more we say it, the more we write it, the more we're going to memorize that word. Circumcenter. Okay, what does the circumcenter theorem tell us then that is congruent in our picture? So go back to your theorem. What's equidistant now? Okay, the circumcenter to the vertices. So name those distances. Not GF, DE, or DG and EG. Those are the perpendicular bisectors. It's the distance from the circumcenter to the vertices that is equidistant. So remember up here, it's from the circumcenter to the vertex, circumcenter to vertex, circumcenter to vertex. So what is that in this picture? GA, GB, and GC. Okay, that's the part you're going to have to get clear in your mind is what can you mark congruent? And if you can mark your picture with all of the things, then the question will be super easy to answer. Because it says find GC. So we're trying to find this distance. What did we just say GC is the same as? GA and GB. And what is GB according to the picture? 13.4. It's pointing to GB. So GC, which is what they want us to find, is just 13.4. So the math's not hard, but it's understanding what you can mark in your picture based off your theorem. Okay, let's look at one more. All right, so same picture, or actually this is a different picture, isn't it? This is different, right? But they're missing information on your notes. So add this to your notes, and it should actually say KZ and LZ are perpendicular bisectors. So you're missing that sentence. I forgot to put it on there. So KZ and LZ are perpendicular bisectors of the triangle. So write that down on that example to the right there. KZ and LZ are perpendicular bisectors of triangle GHJ. Okay, then go to your picture and mark what that's telling you. So KZ is a perpendicular bisector of the triangle. That means I should be able to draw a right angle box on the side of the triangle. And what two pieces should I be able to mark congruent? Very good. GK and HK, a perpendicular bisector of the side of the triangle. LZ is also a perpendicular bisector. So we can draw a right angle box, and what pieces are congruent on that side? HL and JL. Okay, so mark your picture. What does that make point Z then where KZ and LZ meet? Circumcenter. So based off the theorem, what pieces do we now know are congruent? Okay, so remember it's the distance from the circumcenter to the vertices that we now know based off this theorem. So that would be Z, G, Z, H, and Z, J. So those are all going to be congruent. And now we should be able to answer the next couple questions based off this picture because the next two slides are the same picture. So this slide says find GK. So look at your picture. GK is this piece right here. What did we say GK should be the same as? HK. If you look at your markings, we said these should be congruent. So that means if HK is 18.6, what is GK? 18.6. So there's no work there. We just look at the picture, see the parts that are now congruent. I'm not going to remark all of this on the next slide, but if you'll look down on your next slide, what does it ask you to find on the next one? JZ, the line segment, not the wrapper. So JZ. All right, so if you look at the picture, JZ, what is JZ supposed to be the same as in this picture? GZ, which is 19.9. Very good. So notice a little arrow pointed here. JZ is supposed to be the same as GZ, so JZ is 19.9. Do you see how easy the questions are once you can mark the picture correctly? It's the picture that gets the harder part. Okay, for time purposes, I'm going to skip the graphing question for now, and let's go on to the back, and let's start talking about the last point of concurrency, the last kind of line segments. So I'm going to skip this example. You will have to know how to do that, but we'll come back to it a different time. So here we go. Let's talk about the in-center. So now we're going to look at the same idea in our triangle, but we're going to draw in the angle bisectors. Okay? So in my triangle, I'm going to draw in the angle bisectors. That means through every vertex, I'm going to draw in a line that's going to split every angle into two congruent parts. And again, I'm just going to sketch these. I could use a protractor and be more precise, but for time purposes, I'm just going to sketch it. So every angle in the triangle, I'm drawing in an angle bisector. And notice once again, if I did it correctly, that those three lines are concurrent. And that makes this point a point of concurrency. And more specifically today, that point of concurrency of the angle bisectors is called the in-center. The in-center. So this point right here, you're going to have to remember the difference between the names. And again, I'll give you a trick on Friday that maybe will help you. But this is the in-center. And the in-center is made by drawing in the angle bisectors. Okay, and it's going to be kind of the opposite of the circumcenter theorem. So the in-center theorem, let's see if I can help you see the connection here. Circumcenter theorem said if you go through the sides by drawing in perpendicular bisectors, then the point of concurrency, the circumcenter, will be equidistant to the angles, to the vertices, right? So now we're going through the angles to make the in-center. So it's not going to be equidistant to the angles. What is it going to be equidistant to? The sides. So that's what the in-center theorem says. The in-center will be equidistant to the sides of the triangle. But remember, when you draw in those distances, they need to be drawn perpendicularly. So the distance from this point over to this side will be the same as the distance from this point over to this side, which will be the same as the distance from this point over to this side. Okay, so again, if you go through the sides to make the point of concurrency, it's going to be equidistant to the angles. If you go through the angles to make the point of concurrency, it's going to be equidistant to the sides. Do you see how they're similar but just switched? Okay, that's in-center theorem. So in this picture, what color of lines are angle bisectors? Well, Andrea's got it. Is everybody with her? What color are the angle bisectors? The red, because they're splitting the angles into two congruent parts. So what do we call point P? In-center. And the in-center theorem says it's going to be equidistant to the side. So now all of these distances will be the same. Got it? Okay, let's look at same chart here. This time though, on this chart, I want you to write down that all of these lines are angle bisectors because it's not written anywhere. So add that to your notes. The lines in this picture are angle bisectors. You could take time and go through and mark all the little angle bisecting marks to help you see that. Okay, but those are all angle bisectors. So what does that make every point P according to this lesson? In-center. And where is it located? Inside. Do you see that it doesn't matter if it's acute, obtuse, or right? The in-center is always inside the triangle. Different than the circumcenter. The circumcenter was inside if it was acute, outside if it was obtuse, and on the hypotenuse if it was a right triangle. The in-center will always be inside. So if you get some questions on your homework that ask you about where is it located, look back at this chart until you can memorize that. Okay, and then they're going to talk about another circle again. So really quickly, circumscribed circles went around the outside of the triangle, touched every vertex. Inscribed circles are inside the triangle and they touch the sides of the triangle. Do you notice that if I draw an inscribed circle in here, that each of those congruent distances to the sides turn out to be? That is the radius. They turn out to be the radii of that circle. If you look at this picture, distance over to here, distance over to here, distance over to here. Do you see how those are all radii of the circle? Okay, so they're all going to be equal. All right, let's look at least one question of how this will look on your homework. So flip on the back. You should have 2 examples left. And we'll get through at least one of them, maybe to both. First one says, find the distance from P to MN. When you look at the picture, nothing is marked congruent, right? But come up here. MP and LP are angle bisectors, so mark your picture with that information. Yep. So MP is an angle bisector of the triangle. What angle then is it bisecting? M, the big angle M, L, M, N. So you can put little congruent marks then on that angle. It's splitting it into 2 congruent parts. LP is an angle bisector. What angle is it bisecting? L, so you can put little congruent marks here. Okay, so that means, what do we call point P where those angle bisectors meet? Angle bisectors meet at the in-center. And we just learned that the in-center is equidistant to where? The sides of the triangle. So that means the distance from P over here, which they said is how much? 5. That distance should be the same as P over to this side and the same as P over to this side. So the question is, what's the distance from P to side MN? So what's the distance from P over to side MN? 5. The same as it is from P over to ML. The same as it would be from P over to LN. So it's just 5. Okay, here's the deal. We did not get through the last 2 examples, this one and the one I skipped. So I want you to do all of your homework, but on the second page, if it's a question about graphing and trying to find the circumcenter, you can skip that one. And when you get to these kinds of questions, if you're struggling, hang on to those, and then we'll talk about these 2 examples on Friday in class, okay? So I'm not technically going to collect this, but I am going to do a quick spot check to see if you did the majority of your homework when you come into class. So make sure you're doing everything you can figure out prior to Friday. But I won't technically collect it until we get after break, okay? But I'm telling you, I'm going to spot check and see, did you do most of it? So make sure you're doing everything you can figure out. Sorry.